Good morning, everyone. Before we begin, I just want to acknowledge the weather. I know the storm has made conditions outside pretty dangerous. The roads are slippery and the wind is strong, so please be very careful when you are commuting or walking around campus today. Stay safe and stay warm. Also, before we dive into today's material, I want to re-emphasize a fantastic resource available to you this semester, the Shear tutoring. The Wuzhou School of Mechanical Engineering has set up this peer tutoring specifically for this COE3001 course. If you have any questions about the course content, or if you are stuck on a homework problem and need a little extra guidance, this is the place to go. It runs Monday through Thursday from 6 p.m. to 8 p.m. over in the MRDC on the 4th floor. One quick note is that the tutors here are peer tutors. They are not the teaching assistants for this specific class, but they are excellent resources. So please, make full use of my office hours, but also take advantage of this Shear tutoring. It's a great way to make sure you are staying on the top of the material. Alright, let's get started with today's lecture. So, in our last class, we focused on the modern jet engine. We used that as a starting point to this course. We understand the extreme conditions that materials have to endure, specifically high mechanical loads and high temperatures. The real-world example gives us a reason to introduce some fundamental properties and behavior of materials. We need to know whether a material is easily deformed and how it will deform under load. Therefore, we introduced two material properties, which is Young's modulus and Poisson's ratio. When we talk about Young's modulus, we are talking about stiffness. It is a measure of how much a material resists deforming when you pull or push on it, right? Mathematically, this brings us back to Hooke's law, which is a fundamental law of spring in general physics. As long as we are operating below the yield stress, meaning that we aren't permanently stretching or compressing the material. Well, more generally speaking, we are not permanently deform the material, right? The relationship between stress and strain in this range is linear, and the slope of the stress-strain curve is called Young's modulus. Now, notice something interesting here. Look at the curves on the screen. There are different materials. These materials have different strengths, right? Some yield very quickly, while the quenched alloy steel can handle massive stresses. But look at the slope at the very beginning. They all share exactly the same slope. This is a crucial concept for engineers, actually. Strength is not the same as stiffness. We can change a material's strength significantly through alloying, heat treating, or manufacturing process. We can make it stronger and make it harder, but the stiffness, namely the Young's modulus or the modulus of elasticity, is an inherent property of the atomic bonds, and they cannot be easily changed. Well, generally speaking, you can't really change the stiffness of a steel just by heat treating or manufacturing process. Whether it's soft iron or high-strength steel, the initial elastic response always remains constant. When we talk about Poisson's ratio, we all know intuitively that if you take a slender bar and pull on it, it gets longer in the direction of the pull. But that's not the only thing that's happening. It elongates. It also gets narrower. It contracts in the lateral directions. Poisson's ratio simply quantifies this relationship. It's defined as the negative ratio of the lateral strain to axial strain. So, while Young's modulus tell us about resistance to stretching, Poisson's ratio actually captures the coupled change in shape. But we also went deeper than just the engineering definitions. We look at the physics behind them. We discussed how macroscopic behaviors like elasticity and Poisson's ratio are actually the result of interatomic forces, right? It's the collective reaction of atoms pushing and pulling on each other that determines how a material behaves. Today, we are going to build on those concepts. We are going to look at the two most fundamental ways a physical body can deform, which is the axial deformation, namely tension and compression, and sliding deformation, namely shear. Now, let's formally define normal stress and normal strain. I want us to take a step back and think about what these terms really mean. Often in engineering, we get lost in the formulas. Sigma equals P over A, epsilon equals delta over L. But I want you to focus on the physical process. Stress and strain are simply mathematical tools we invented to describe a physical reality. When you pull on that bar, the atoms are physically moving apart. Normal stress is just our way of averaging that internal resistance perpendicular over a specific area. Normal strain is just a way to quantify that physical elongation, right? We use stress and strain to eliminate the size effect, and let's focus more on the material itself, right? That's the reason we don't use force or displacement. Now, look at the text in red on the slide. This is the sign convention. We define tensile stress, namely pulling, as positive, and compressive stress, namely pushing, as negative. I want to emphasize this is not a law of physics. Nature doesn't care about plus or minus signs. It only cares about forces. Right? This sign convention is a human agreement. We established this rule just to make our communication consistent, and our calculation convenient. So, when you see a negative sign in your answer, don't panic. It just physically means the material is being squeezed. I have put a simple practice problem on the screen. We have a hollow aluminum tube supporting a compressive load, and I want you to determine the compressive stress and strain. Well, to find the stress, it's a direct application of our formula, force divided by area. The only thing you need to watch out for this geometry, since it is a hollow tube, right? Make sure you calculate the area of the solid ring. It's actually the outer circle minus the inner circle, right? It's not the whole disk. To find the strain is simply the change in length, actually 0.55 millimeter, divided by the original length of 1 meter, right? Just be careful with our units. Millimeter is 10 to the negative of 3 meters. So, substitute all this quantity into the formula. The definition of stress and strain, we can calculate the stress and strain itself. If normal stress is about pulling and pushing, shear stress is about sliding. I want you to look at a diagram of the belt connection on the screen. When you pull on those plates, the belt isn't being stretched, right? It's being sliced. The force is acting tangentially to the cross-section. That is shear stress, and we denote it with the Greek letter tau. Tau is actually T-A-U, right? Now, because the force is different, the deformation is also different. Normal stress causes elongation, making things get longer or shorter, while the shear stress causes distortion. It causes an angular change. Look at the red box on the right side of the slide. Originally, that was a perfect square with 90-degree corners. When we apply shear, it tilts. It becomes a parallelogram. That change in angle, the deviation from 90 degrees, well, actually the tangent of the angle is what we define as shear strain. Remember, the shear strain is also the change in length divided by the original length. So the change in length is actually how long it will move. It moves, right? The original length is the side length of the square. So we get tangent of the angle, right? But for very small angles or very small deformations, the tangent of theta is basically equal to theta itself. So we simplify our lives and just say, okay, gamma equals theta. Now a quick note on the sign convention. Usually, this is where we should define positive and negative shear. However, the sign convention for shear is a bit more complex than tension and compression, and it really matters most when we start twisting things. Right? So to avoid mixing up concepts and confusing you right now, we are going to hold off on the strict sign convention for the shear until we reach the torsion section later in this course. For today, I want you to focus on the physical mechanism, the sliding force, and the change in angle. Just like we saw with Young's modulus, Hooke's law also applies to shear. For small deformations, there is a linear relationship between shear stress and shear strain. The slope of that line is defined as the shear modulus G. Crucially, G isn't independent. It can be calculated using Young's modulus and Poisson's ratio. The derivation of this relationship belongs in a more advanced mechanics course, so for now, I just want you to memorize this formula or add it to your equation sheet. You will need it for future calculations. G equals Young's modulus E over 2 times 1 plus Poisson's ratio mu. Following up on Hooke's law, I want to address a critical concept regarding equilibrium. Ask yourself, can a shear stress exist on just one pair of faces? Look at the cube on the slide. If we only had shear forces on the top and bottom faces, think about what will happen. The element won't just deform, it would start spinning, right? It would violate the moment equilibrium. To prevent this rotation or this spinning, nature requires a balanced pair of shear stresses on the vertical faces. This leads to a fundamental rule, equality of shear stresses on two perpendicular surfaces. Shear stresses on perpendicular planes are always equal in magnitude. Well, visually, an easy way to remember this is that the arrows that the corners always meet. The arrows at the corners always meet. The arrows are head to head or tail to tail, because you need a counteraction to balance the moment generated by one pair of shear forces. Right? Okay, since we touched on this in the last lecture, let's just do a quick recap of the stress strain behavior of a mild steel. Looking at the curve, you will recognize the 4 distinct zones. Well, the first zone is the linear region, while the second one is a perfect yielding or perfect plasticity. Well, the third region is the strain hardening, and the fourth region is necking. The most critical thing to remember for today is unloading. Right? If we load the material into the hardening zone and then let it go, it doesn't retrace the curve. It unloads along a straight line that parallel to the original elastic slope. This means it unloads with the stiffness of Young's modulus. You recover the elastic strain, but you are left with permanent plastic deformation. Finally, a quick reminder on true stress and nominal stress, as indicated by the dashed line and the solid line. Physically, we know the cross-section area shrinks as we pull because of Poisson's effect, which increases the actual stresses. That is called true stress. However, in this class, we stick to nominal stress. That means we're using the original area. Why? Because we assume small deformations. In that range, the change in area is negligible, so nominal stress is accurate enough for our design needs. Now here is the catch. The stress strain curve we just look at for mild steel or structural steel is actually a bit of a special case. It has a very clear, sharp, distinct of yield point, right? Remember the plateau. It makes our life easy because it's obvious exactly when the material stops behaving elastically and starts yielding. But here is the reality. Most materials are not so cooperative. On the left, we have the stress strain curve for an aluminum alloy. Notice the difference? There is no sharp transition. It curves over gradually. It transitions from elastic to plastic behavior so smoothly that if I ask you to point to the exact spot where the yield begins, you'd just be guessing, right? Virtual inspection isn't enough, but as engineers, we need a specific number. We can't design a safe aircraft wing based on our guess, right? We need a defined yield strength to ensure safety. So how do we define it? We use the method of offset, or sometimes people call it offset method. This method connects directly back to what I just told you about unloading. Remember how the material unloads along a straight line parallel to the elastic slope? Well, the offset method use that geometry to create a standard definition. Here is the procedure, and it's the industry standard for materials like aluminum and titanium. First, we define a specific amount of plastic strain that we consider significant. Right? Usually that is 0.2% or 0.002 strain, right? Then we mark that 0.002 strain point on the x-axis because the x-axis represents the strain, right? Followed, we draw a straight line from that point, moving upwards and parallel to the initial linear elastic part of the curve. Where that dashed line intersects the stress strain curve, that is your defined yield strength. So even though the material doesn't have a sharp physical yield point, we have mathematically created one so that we can design the safety. So far, we have been talking about materials with good extensibility, what we call ductile, right? But there is another class of materials that behaves very differently. These materials exhibit very little deformation. Instead of stretching or yielding, they tend to fail by sudden fracture. We call this category of materials brittle materials. The brittle materials typically include glass, ceramic, concrete, cast iron, and so on. Their main character is that most of them are relatively inexpensive, right? Yeah, typically inexpensive. Now, you may be thinking, if these brittle materials just snap without any warning, why on earth we still use them? It sounds like a terrible idea to build a bridge or a building out of something that fails suddenly, right? But here is the redeeming quality of brittle materials. They are sufficiently strong in compression, at least compared to their price, right? Because they are relatively inexpensive. Let's look at their compression behavior. First, let's look at ductile materials, like steels, right? In the initial elastic stage, tension and compression look basically the same. But once you pass the yield point, the compressive situation diverges, right? In tension, as we saw, the material necks down, gets thinner, and eventually breaks. But in compression, it does the opposite. It bungles out. It gets flatter, and fatter, right? Because the cross-sectional area is actually increasing, it can actually support enormous load without fracturing. Well, typically it just flattens out like a pancake, right? Now let's look at the brittle materials. This is where the magic happens. In tension, these materials are very weak. They crack easily. But in compression, their ultimate strength is massive, often many times higher than their tensile strength. This is why we build foundations out of concrete and arcs out of stone, right? We design the structure specifically so that the material is always being squeezed under compression and they are never being pulled or tensiled or tensioned. As long as we keep those materials in compression, they are among the most efficient materials we have. Think about the stone, right? The stone is so cheap, so inexpensive that everywhere is a stone. So if you build the foundation with stone, it won't cost you too much, and you have a strong enough foundation for your building. Now, let's apply all of this knowledge to a simple structural design problem. In this exercise, we are given 4 structures. The cross-sectional area, the beam length, and the geometry are exactly the same. The only difference is which members are made of iron and which members are made of steel. So take a minute to think about it. If you were the designer, you want to design such a structure, which material you will choose for a specific beam? Yeah, please take a pause and think about this question. I will just continue. Well, from the material behavior, we know 2 important facts. The cast iron is brittle and is best used under compression, right? The steel is ductile, as the steel performs well in both tension and compression. So when we examine those structures, we should assign materials based on the type of loading in each member. Members that primarily carry compression can be made of iron. Members that carry tension should be made of steel. Using this reasoning, structure B and D are acceptable choices because the upper beam usually under tension and the lower beam, the horizontal beam, is typically under compression, right? However, at this time, structure B and D are acceptable choices, but there is an additional consideration. In the last session of this whole semester, we will learn that compression members should be as short as possible to avoid buckling. Remember, buckling is a loss of stability, right? Taking this into account, structure B is actually the most reasonable choice. Well, why? Because the iron is under compression, right? We want to make the iron beam as short as possible. Therefore, D is not so suitable for this kind of structure. Therefore, B is the best choice, and B and D are acceptable choices. Next, I want to introduce a concept that challenges a basic assumption we have made so far. I want you to look at those high voltage power lines. We usually think of metals like steel and aluminum as being incredibly stable, right? If you build a steel beam, you expect it to stay there forever. So why do these transmission wires have a service life? Why do utility companies have to go out and replace them every 30 or 40 years? They aren't necessarily rusting away, right? So what is happening to them? The answer is a phenomenon called creep. Up until now, we have assumed that if you apply a load to a material, the deformation happens instantly and then stops. You pull it, it stretches, and that's all, that's it. But in reality, especially over long periods of time or at high temperatures, materials behave differently. Creep is the tendency of a solid material to move slowly or deform permanently under the influence of mechanical stresses. Well, the instant deformation is somehow a kind of idealization. The creep happens everywhere, even under elastic deformation, right? Because your material is not perfect. Even though the overall response is still within the elastic range, at some local points, for example, the local region that's near some defects, like you have some bubbles in your wire or you have some micro cracks in your wire, near that local region, you may still go into the plastic region. The plasticity happens with when the time goes by, right? At a very, very long time, the plasticity always deform your material and make your material deform permanently. For those kind of power lines over years of handling, right? Remember, handling, over years of handling under their own weight, the wires physically get longer due to the creep, causing them to sag dangerously lower. This is why these materials have an expiration date. They aren't breaking, they are just slowly, inevitably changing shape until the shape is unacceptable. Now I want to quickly wrap up by showing you that failure actually looks like. If you pick up a broken part in the field, you can often tell exactly how it failed just by looking at the fracture surface. First, let's look at ductile fracture. Because ductile materials deform significantly before breaking, in the fracture, it creates a very specific shape. We call this the cup and cone fracture. It looks rough and fibrous. If you were to put this under a microscope, you will see these little dimples where microvoids formed and coalesced as the material stretched. Well, basically speaking, when you pull the material, right, you elongate it. First, there are some voids generated, as indicated by the figure B, right? Then the voids coalesce and form a micro crack, right? And then the crack extends. But you know that the ductile material can sustain a lot of normal stress, but they are easily shared because think about the atom. The atom can easily be shared with respect to each other, but it's very hard to pull apart. Therefore, the crack will extend along the 45-degree maximum shear stress direction. Right now, I just tell you, okay, 45 degree is very dangerous. At the end of this lecture, I will go through a quick example. Therefore, you will understand why 45 degree is dangerous. Then, the crack propagates, elongates along the horizontal or the 45-degree direction, and then finally, eventually, the material fractures. And if that time you look at the fracture surface, the dimple is just the microvoids generated at the very beginning. Well, contrast that with brittle fracture. This is what happens to cast iron or glass. There is almost no deformation or no necking. The failure is abrupt. Consequently, the fracture surface is usually flat and shiny. You can see the picture that the fracture surface is very flat and it looks perfect, right? The crack just slides right through the material grains or along the grain boundaries without any warning, right? Like you can say that there's two different kinds of fracture. One is the transgranular, means the crack that extends or right through the material grain. Well, the grain is somehow more advanced concepts I will introduce later. Right? You can just say, okay, all the crystal materials are made of grains, and the grain have different orientations. That's all. Okay, to wrap up today's lecture, I want to lead us through a quick exercise. This ties everything we have talked about together. We usually think about stress acting on a perfect vertical cross-section, but in the real world, materials often fail along weak planes that are at an angle. Remember, 45-degree angle. Why? Right? So let's look at the example. We have a bar under simple tension P, but instead of cutting it straight down, we are analyzing a cross-section PQ that is inclined at an angle theta. Remember our fundamental definition. Stress equals force divided by area. So I want you to find the stress on this sloped inclined plane. We need to know two things, right? Because stress equals force divided by area. First, we need to know the magnitude of the normal force and the magnitude of the shear force. Because normal and shear forces acting differently. One is tension compression, one is distortion, right? And also, there's another quantity that is area, right? If the cross-section is inclined, it's not perpendicular to the axial direction, we need a new area, right? Where we cannot use the cross-sectional area directly, right? We need these two quantities to find the stress. So take you some time. Maybe I will give you 4 or 5 minutes to finish this problem, this exercise. And please take a pause here, and I will continue to the next slides, the answer. But make sure you finish this exercise problem on your own, and then you go to the answer and solve this question together with me, so that you can have better understanding for this kind of problem. Okay. First, let's look at the geometry. We want to know the cross-sectional area for the inclined section, right? When you slice a bar at an angle theta, the cut surface is larger than the original cross-section, right? If your original cross-section area is A0, then using simple transformation of the using simple triangular transformation, the area of our inclined face is the area of our inclined face A is actually A0 divided by the cosine theta. Why? Look at the triangle, the black triangle on the screen, right? The vertical line has a length of A0, right? Oh, sorry, the area as A0. You know that A0 over A is actually equals cosine theta. Therefore, you can calculate A equals A0 over cosine theta, right? That's the force. Since cosine theta is always smaller than 1, therefore, the area A has increased. The step 2 is to calculate the forces. Next, we look at the equilibrium. The external force P is horizontal, but to find the stress, we need the force that are perpendicular and parallel to our new cut surface. So we need to decompose the force P. The normal force N is acting perpendicular to that cut, which equals P times cosine theta. The shear force is sliding along the cut, which equals P times sine theta. Right? This is a simple decomposition of forces, decomposition of vectors to the vertical and parallel directions. Right? With that magnitude of normal and shear force, with that magnitude of the cross-sectional area, we can calculate the stress. Now we just do the deviation, right? And here is the final answer, right? The normal stress equals N divided by A equals P over A0 times cosine squared theta, right? Remember, cosine squared theta equals 1 plus cosine 2 theta. It changed the periodicity of the triangular function, right? It's positive or negative, right? Look at the figure. We decompose the force, and we find, okay, the normal force, that for force perpendicular to the cut surface, is actually point outward, which means the bar is under tension, right? Therefore, you will have a positive, of course, you will have a positive normal stress, right? So there's a plus sign at the very beginning, but it can be hidden, right? And the shear stress equals the magnitude of shear force divided by the new area is actually V over A. Remember, we haven't talked about the sign convention yet, but if you consider about the sign convention, there should be a negative sign here, right? So it's negative V over A equals negative P over A times sine theta times cosine theta. And you can use the triangular function to get, okay, it equals, the sine theta cosine theta equals half sine 2 theta, right? So you get this function, this two functional form. Finally, if we put these stress functions against the angle theta, we will see something very important. Look at the graph. You can clearly see the shear stress reaches its maximum value exactly at positive and negative 45 degrees. That's why I said in the ductile fracture, 45 degree is the most dangerous angle. This explains a phenomenon you will often see in the lab, right? The material falls at a 45 degree angle, as illustrated on the experimental figure on the very right of the slide, right? Even when they are just being pulled or pushed straight, right? You apply an axial load, but you get fail on a 45 degree angle. Why? Because even though the load is axial, the internal mechanics generate a peak shear on the 45 degree plane as we calculated, right? If the material is weak in shear, that is exactly where it will break. Okay, one quick note on the math before we go. You might have noticed that in our derivation just now, specifically when we went from the square terms to the double angle formulas, I skipped a few algebraic steps. I did that intentionally because I assumed that you have all had extensive practice with these trigonometric identities in your calculus course. I expect you to be reasonably comfortable with those transformations. However, if you feel a little rusty or if you find yourself struggling to follow those specific steps, please take a look at this review slide. It covers all the fundamental definitions and identities you will need to manipulate these equations. Make sure those are fresh in your mind, because we will be using those kind of functions or equalities frequently. Alright, that's all for today. Stay safe and stay warm, and I will see you in the next lecture. Oh, by the way, because this is a modified operation and I have to record everything, so we miss a lot of interactivities on the class. Therefore, I will review everything in this course, in this lecture, later in the next lecture after we recover the in-person lecture. Okay, that's all for today. Thanks for your listening, and looking forward to you in person in the future lecture.